Good afternoon, everyone. Thank you for coming by after lunch today and learn more about dates and time. I am delighted to be here in the United Kingdom, where yesterday you all sent your Prime Minister out into a rain-drenched emo music video to announce that you're having elections in 6 weeks. Somehow he's got more dignity getting completely soaked than the prior Prime Minister, who served as an inspiration for my wife's 2022 Halloween costume, which gave me a really excellent excuse to break out my laser cutter and make the podium and the googly eyes for the lettuce. Now, as an American, I'm very jealous that you all get to have your elections over in 6 weeks, as our campaigns tend to go on for an inordinately long time and feel like they go on for even longer than that. And as a Yank, I'm also extremely amused that you've all decided to have your elections on the 4th of July, the day that we told you a lot to get out and stay out 248 years ago. And I did see that there's already one candidate taking proper advantage of that fact in their campaign. I'm sure there will be more right behind them. Now, it's time for the actual talk. Speaking of which, time. Time seems really straightforward when you first start working with it. And since this is not a lightning talk, you will probably not be surprised to learn that it absolutely is not. But when you start, you think, okay, I have the current date, and I want to add an hour. So once you find out that under the hood, a date is generally a representation of time in seconds, you think, okay, to add an hour, I'll just say that I need to add 60 seconds, then 60 minutes. And to add a day, I'll just multiply that by the 24 hours in a day. And then for a year, just multiply that by the 365 days in a year. And so you go ahead and set up some code to grab the date, turn your calculated number into a time interval, add it together, and then print it out. And if you did this anytime in the months of January or February this year, when you ran it, you got the correct answer for that particular day, but you've been off by a day for a year later. That is because 2024 is a leap year, here to throw all of your simple calculations straight into the trash. And you start to think, this may be harder than it appears. And it turns out that if you try to think of every single thing that needs to be taken into account when figuring out how to represent a time stored in a computer in a way that makes sense to humans, you wind up sounding like you're slowly losing your mind, and there's a fairly decent chance that you will feel like you're slowly losing your mind as well. So I want to start with what a computer thinks a date is, and what Swift in particular thinks it is. So it's represented as a good old date. Now, Apple defines a date as a specific point in time, independent of any calendar or time zone. And this is all well and good, but this clearly got some spoilers about other things we're going to be talking about later. So if you want a spoiler-free version of this, you'll have to go with my definition of a date, which is that it's a fixed point in time. And some of the methods on it give you an idea of how that fixed time is represented under the hood, because when you see something like time interval since 1970, you think, aha, this is when computer languages really started coming into more common use. Maybe everyone just agreed that this was the beginning of time at that point. And that's basically what happened. This is known as the Unix epoch. But then the foundation developers at Apple found that they also had to start accounting for all the programmers who were born well after 1970. And they came up with the more loosely named reference date, I assume because they didn't want anyone to think too hard about what year it actually was under the hood. Which is probably good, because while the place where the time interval since 1970 starts is midnight UTC on the 1st of January 1970, the reference date could have been anything. Instead, they selected the 1st of January 2001 at midnight UTC, because apparently somebody thought just putting it on the border of 2000 would be way too easy. Now, once you've been staring at these dates for a while, you start to see them jump out everywhere, especially when they get into a weird state where they're calculating data based on 0. In fact, when Greg Pierce of Drafts fame tweeted about Apple somehow knowing where his 22-year-old was a year before he was born, my antennae went up, and I took a look at the timestamp. So someone who was 22 in 2024 would have been born in 2002. A year before that is 2001. And I bet myself $1 that if I went and I put in the dates, I would, and I did in fact, get exactly the same number of days as it would have been from the reference date. And I was able to fairly quickly reply the time interval since reference date was the source of his son's potential time travel issues, and feel incredibly smug about having figured that out. Now, Going back to the two main time intervals, why would Apple randomly decide to do something 31 years in the future? Because they knew that most dates are actually stored under the hood as a signed 32-bit integer reference to a time interval in seconds since a given date. And for the time since 1970, that integer is actually going to overflow in about 14 years. And since it's based on the Unix epoch, some folks are, of course, referring to this as the epocalypse. People who work on longer term planning software are already starting to run into problems with this for time referencing 1970. And Apple thought, well, this is a problem for future us. When the rest of the world will already have to switch to either a new reference date or a 64-bit integer, we'll just be over here sitting pretty with another 39 years before this becomes a problem for us. And when folks do transition dates to 64-bit integers, they won't overflow for another 292 billion years, which is 21 times the estimated age of the universe. So it will definitely be somebody else's problem by then. And because very few places have managed to move off the 1970 standard so far, Apple added a convenient static method for figuring out the diff between the two commonly used reference dates on the platform. I'm going to save you opening a playground to find out. It is a difference of 978,307,200 seconds. Fun facts for pub trivia in the world's dorkiest pub. That count of seconds is basically the way that computers think about dates, as a monotonically increasing number of seconds since a fixed point in time. But as I said, that is absolutely not the way humans think about time. There are a lot of pieces of the puzzle to figure out how to take these fairly basic structures of a count of seconds since a given time and translate them to something that people will actually understand. And a good place to start with this is the calendar. So Apple says that a calendar is a definition of the relationships between calendar units and absolute points in time, providing features or calculation and comparison of dates. What I say calendar is the only way to relate an absolute point in time to anything humans will actually be able to understand. And this is where the messiness of humanity starts to really rear its ugly head, especially in the form of days that just flat out don't exist in the middle of calendars. Because for many of us used to dealing with international communication, we think of the calendar in terms of 12 months, most either 30 or 31 days, but then there's one weird one that's usually 28, but sometimes 29. When we're talking about that calendar, we're primarily discussing the Gregorian calendar. And let me nerd out more than a little bit here, because I'm just fascinated by how various things we take for granted came to be. So it's called Gregorian because in October 1582, Pope Gregory XIII finalized the reforms that led to this system that's used fairly internationally now. The main calendar in use before that in the Christian world was the Julian calendar. And if you've ever been dealing with a particularly nasty bug caused by leap years and thought, man, I could just stab the jerk that came up with leap years, I have good news for you, because the Julian was Julius Caesar. So thanks, Brutus. Anyway, the Julian calendar calculated that the Earth rotated around the sun every 365 and a quarter days. And so to correct for that unevenness, you just kind of crowbarred an extra day in every 4 years to make things balance out. Easy peasy, right? But the Romans were not quite as good as astronomy as they thought they were, because it turns out that in reality, the Earth actually orbits the sun just a tiny bit less frequently than they thought. Not terribly perceptible over the course of a few years, but the difference meant that the calendar would drift off by about 3 days every 400 years. And there had been a few attempts to adjust for this, but by the time of the Gregorian changeover, the Julian calendar was off by almost 10 days from where the equinoxes, or points where day and night are the same length, were actually taking place. So good old Greg over here approved some changes to the calendar that bears his name, including removing 10 days so that the calendar went straight from October 4th, 1582 to October 15th, 1582. And there wasn't anything particularly special about those dates. In fact, it's so arbitrary that if you look at the open source version of Foundation, you'll see that the Gregorian calendar is actually hard-coded to begin on October 15th, 1582. And most countries have since adopted the Gregorian calendar for civil use, although some of them with their own local twists that will absolutely kill any math you think you're doing. For instance, in the Japanese calendar, everything is identical to the Gregorian calendar except the year. The year is instead calculated by what year of the emperor's reign it is. And this leads to all kinds of fun problems when an emperor dies, or in the case of Emperor Akihito in 2019, abdicates. So the day that he abdicated was April 30th, Heisei 31. And his son, Naruhito, took the throne the next day, and the next day was May 1st, Reiwa won. So for Heisei 31, anything after April 30th doesn't exist. And for Reiwa 1, anything before May 1st doesn't exist. Whole swaths of months of dates, and they're just gone. And all that is before you even start dealing with lunisolar calendars, which are calculated by how frequently the moon orbits around the Earth, rather than how frequently the Earth orbits around the sun. But then, in order to line back up with solar calendars like the Gregorian calendar, they have an entire extra month shoved in every few years. And obviously, trying to keep track of all of this is absolutely maddening. So one of the earliest things you learn when you're dealing with dates is that you absolutely should not try to manage all of this yourself. Apple has done a whole lot of work to get all of this as right as they can. And at least if they've messed it up, you can always blame it on them. So what are the conveniences that Apple provides for this? To get a specific calendar, you just pass its identifier into an initializer. That's pretty straightforward if you actually know what calendar you want to use for something. But most of the time, your user will have a particular calendar that they usually work with, which may or may not be the same as the one that you usually work with. So how do you know how your user wants to see things? The easiest answer is to grab the auto-updating current calendar from the system, because that will give you a lot of information about what sort of calendar the user wants to see things displayed in. Okay, great. Now that you know how to get their preferred calendar, what do you do to actually display a date? This is where we run into our friend, the date formatter. And the Apple definition of this is that instances of date formatter create string representations of date objects and convert textual representations of dates and times into date object, where I say it is the thing that you should use to turn a date into a user-facing string. And this is where all these pieces start to come together, because the way you tell a date formatter what calendar it should use to display things is by just handing it that calendar directly, telling that formatter to generate a string based on that calendar. And lo and behold, when you run this, you get absolutely nothing. And that's because the formatter knows what calendar you want something displayed in, but it has no idea what actual information you want to display. And you could hand it a raw date format string. It'll print out exactly what you tell it to, no matter where someone is located. I found this is mostly useful for moving back and forth between dates and strings, especially from APIs, where you know what the format is going to be, but you also know it's not going to be something standardized like ISO 8601. Now, if you plan to do this, I highly recommend Ben Sherman from NS Screencast public service site, nsdateformatter.com, which I cannot even tell you how frequently I reference this when I need to remember how to write a format and not have it accidentally use minutes instead of months. While having a very specific format is sometimes what you want, something you're going to want far, far more often is to use one of the Apple-provided date styles. Because in addition to having sensible defaults, you can also adjust the output based on locale. So if I just grab the auto-updating current calendar like I did here and tell it to use the full date style, it realizes I'm in the UK and outputs the date in a format that makes sense for the UK. However, I can also pretend I'm back in the United States by setting a specific locale on the formatter, and then it will print the date I handed in Murica format without me really having to do anything else. The other thing you can do is if you definitely know you want to print something in a particular calendar, you can set up a formatter which is instantiated specifically with that calendar. In this case, we're going to use the Islamic calendar. And again, if you give it a date style, it'll print something that makes sense for your current location. But you can, again, hand it a specific locale so that it prints in exactly the format you want it to. Now, in addition to the primary date formatter, there are several other useful date formatters that you may want to look into for the specific use cases that they handle, so you don't have to. A date interval formatter is really, really useful for displaying how long a date time period is between two different dates. Date components formatter is basically what it says on the tin. It takes a set of date components and formats them. This is really, really useful for APIs that return a set of date components rather than a date, and I'm going to talk about date components in a little bit. The ISO 8601 date formatter is very useful for going back and forth between dates and strings that match the ISO 8601 format, which, if your backend team prefers to not be in constant pain, is probably the best way to send dates as strings for an API. Finally, there is the relative date time formatter, which for some reason is only available in Swift. And it'll take a date to compare, then a relative date, and format it for things like 1 hour ago, yesterday, tomorrow. If you're writing a social media client, you are going to get very, very familiar with that formatter. Now, so far, I've talked about the standard formatter classes that have been in iOS for ages. But more recently, we've seen some additions in the form of pure Swift formatters using format style. Now, one of the big reasons for this was that when you're using the older style formatters, instantiating them is, for reasons I don't entirely understand, really expensive. However, format style has a bunch of optimizations under the hood that make it considerably cheaper to use, which is good for things like SwiftUI that wind up creating and instantiating and instantiating and instantiating and instantiating things all the time. Now, I will admit that I haven't worked with these extensively because I tend to do most of my work on formatting outside of SwiftUI in something in the neighborhood of a view model. However, I do want to point you to one really useful resource for this, although I do not want to cause anyone to faint from the impropriety and impertinence of its actual name. So I will point you to the family-friendly mirror at goshdarnformatstyle.com. This is actually a really, really excellent resource with tons of examples well beyond date formatting, and it has a lot of really useful explanations of how you can use default format styles to do something reasonably sensible and localized, or you can use default instances of format styles to do something more specific, or you can even instantiate your own format style that lets you do things like specify the time zone you want to format your date in so that you can know it's still the old year in the US when it's the new year in GMT. There's also some fairly cool things that are quite different than the existing UIKit formatters, like being able to format a Swift range of dates rather than having to explicitly specify which one's the start and which one's the end. Now, one thing that, depending on how you look at it, is either a benefit or a drawback, is that almost all of this stuff heavily uses type inference to let you know what you can do on any particular type. You can get into some weird states where, unless you know that you have to call an interval formatter on a range of dates, instead of passing those dates to the formatter, you can wind up pretty stuck if you're not consulting a resource like goshdarnformatstyle.com. Anyway, now that we talked about how to turn a date into a user-facing string, how to turn a string into a date, let's talk about turning that date into its component parts. And you will be shocked to hear the way that this is represented in Swift is through the date component structure. Apple's definition is that date components are a date or time specified in terms of units such as year, month, day, hour, and minute to be evaluated in a calendar system and time zone. And we've talked about calendars, but we've only briefly touched on time zones, which we're going to talk about more later. So the spoiler-free version of this is that date components are the way that you define which parts of a date you actually care about. And one way to see what I mean by that is to look at the initializer for date components, which tells you not only what the various parts of a date are that could be part of a date components object, but it also provides an excellent excuse to throw yet another meme in here. No. What it actually does is tell you that in any date component objects, these things could be there or they could not. And when you're working with a calendar, there are two ways you can work with date components. You can get a set of components out of a date, or you can get a date from a set of components. So we'll start with getting components out of a given date and time. So the example I'm going to use, the time this talk was scheduled to begin, Thursday, May 23rd, 2024 at 2:30 p.m. British Summer Time. And I want to know, if all I want to know is what the hour and minute are, then I can just ask for them by passing those components in as part of the set that I want back. Then when I query that set of components for the hour and minute, I'll get those back as optionals with a value since I explicitly asked for them. However, if I ask the date components object for a component that wasn't one of the ones that was part of this set of components that I've passed in, such as the second component, when I try to print that, it will wind up returning nil. So just remember, you will not get a component unless you specifically ask for it using this API. So that's getting components out of a date. Let's talk about turning a set of components into a date. So if I want to take the year of 2024, the 5th month and the 23rd day, and then turn them into a date using the Gregorian calendar, then use a formatter I've set up with the Gregorian calendar, I will get everything coming out the way that I want it to, because all of my operations are taking place in the same calendar. Now, One thing that's interesting is starting to add a format for the time style. And you'll see that because you didn't pass in any time components, the time registers as midnight. Or if you're going 24-hour time instead of AM PM, 0 hours. In fact, if you just take away all the components except for the year, you'll wind up with January 2024 at midnight. January 1st, 2024 at midnight, because those are the first valid values of each of the nil components that were passed into the calendar. And you can, of course, pass in more components to do things like get the exact time that this talk was scheduled for. Now, let's back up a second and forget about time and go back to working with just dates for a minute. Now, if you take these components and say, okay, I'm going to try to use the Islamic calendar to make a date from these components, but then I'm going to use a Gregorian formatter to print it back out so that I can see if the components that I passed in create the same date. And what you'll get is that the date you've created in the Islamic calendar is now several hundred years in the future in an entirely different month and an entirely different day number. Why is that? So it's easier to see when you take that same result and print it out with a formatter you've handed the Islamic calendar, which will tell you that it's the 23rd day of the month of Jumada 1, 2024 years after the Prophet Muhammad migrated to Medina. And the fact that the day and the year match what those components are should tip you off to what's happened here. You gave it components that were designed to be used with the Gregorian calendar, but you handed them to an Islamic calendar. That Islamic calendar has different baselines for everything. So the absolute point in time it creates based on those components is going to be different. It's still the 23rd day of the 5th month in the 2024 year after what the calendar deems 0. But because the Islamic calendar starts several hundred years later than the Gregorian calendar, if you hand Gregorian date components to an Islamic calendar, then format the resulting date with a Gregorian calendar, you will get something that is basically the Gregorian date plus the amount of time until the 0 of the Islamic calendar. Now, in theory, a way to deal with all of this is to pass a calendar into your date components object, and according to the documentation, that will tell the receiving calendar what the original calendar was for the components being passed in. In the real world, this does absolutely nothing. You can confirm this by looking at the logic of date from components in the open source version of the Foundation. Calendar component, completely ignored. I have no idea why, particularly since the docs explicitly say it shouldn't be. So to properly change a date from one calendar to another, you really have to use the calendar in which you've created your components to create a date object that represents a specific point in time, then hand that specific point in time over something else working with the other calendar to translate it to something users of the other calendar can understand. So now I want to discuss one more weirdness that people have imposed on dates and time. We're going to start by heading back to this slide. And you probably noticed something in here a couple of times, and that is the abbreviation UTC, which stands for Coordinated Universal Time. However, because the abbreviations don't match up and that makes me twitch very, very hard, I tend to think of it more as universal time, coordinated. It's a way of representing that time overall is just constantly increasing, never decreasing or changing or dealing with human representations of time. And the fact that no matter where you are on this big, weird planet of ours, spinning out in space, having different parts light and dark at the same time, you can represent time in the exact same way is very convenient for working with computations. So why do we need coordinated universal time? Because humans invented something called the time zone. And this is where our concepts of space and time start to come together. Because as Apple says, a time zone is information about standard time conventions associated with a specific geopolitical region. The way I put it is that a time zone is the way that humans reconcile the rotation of the Earth and a need to coordinate time across physical and political boundaries. Again, I'm going to get a little bit into the weeds of history here, but you can basically blame railroads and the telegraph for the existence of time zones. Before time zone was invented, noon was determined by whenever the sun was at its highest point for the day. And at the speed a horse and carriage could go, you couldn't really travel all that far all that quickly. So every area looking up and going, yeah, it's about the middle, worked pretty well. But once you introduce railroads into the equation, something that used to be a journey of at least a day, such as the journey from Boston to New York, became a matter of hours. And the roughly 12-minute difference between solar noon at one and solar noon at the other meant that if you set your watch in Boston, you'd be 12 minutes early for your train that left at noon in New York because you thought it was 12 minutes later than New Yorkers thought it was. But if you set your watch in New York, your watch showed it being 12 minutes earlier than the Bostonians thought it was. And if that train left at noon Boston time, you would probably miss it. So the idea of having one area where the time was always the same, regardless of the exact position of the sun in the sky, was born from railroads. So people could more reliably figure out when a train was going to show up. Here in Britain, since the country isn't that large, they invented something called Greenwich Mean Time, which basically said, right, we're telling the whole country they're setting clocks to noon whenever it's noon in Greenwich, and they're either going to like it or lump it. But then the telegraph was invented to allow nearly instant communication across very long distances, across entire continents and even oceans. So there became a need to coordinate time across much larger swaths of the world. And while you can see the time zones here have taken a lot of zigs and zags across what are generally political boundaries over the years, if you trim this down to just the very bottom, you can see where this idea started. For every 15 degrees of change in longitude, a new time zone would occur, and it would be an hour later. So why 15 degrees? Because if you divide the number of degrees of longitude that exist by the number of hours in the day, that's what you get. So if you offset for an hour for each time zone from GMT, when you get all the way back around the Earth, the hour would get wrapped around to the next day. Over the years, this has gotten considerably more complicated than just looking at what latitudes are where. In fact, I can tell you that this particular map is at least 13 years old because it shows Samoa and American Samoa in different time zones. That is no longer the case. In fact, they're on opposite sides of the international date line, which is the point where it goes from later in the day behind UTC to earlier in the day ahead of UTC. So American Samoa was initially on the behind side of the international date line because of their history as an American colony, and the United States is on the behind side as well. Also, as an aside, I love that American Samoa denotes the American bit by just putting a bald eagle, which absolutely does not exist anywhere near American Samoa on their flag. Anyway, in 2011, they decided that because they did way more trade with Samoa and Australia than with the United States, because those are far closer physically, they wanted to switch which side of the international date line they were on to be closer to their trading partners temporally. So they just went ahead and skipped a day. In the story, the BBC wrote, as the clock struck midnight, as 29 December ended, Samoa fast-forwarded to 31 December, missing out on 30 December entirely. Which means the fact that this BBC story about it is dated 30th of December 2011, the exact day which did not exist in American Samoa. I find that very entertaining. And then, remember how I said that a time zone is related to the rotation of the Earth? Well, we're still mostly talking about the Earth for now. There is now an official proposal for coordinated lunar time, the name following the same absolutely maddening abbreviation pattern as coordinated universal time. And this is because so many countries and companies are launching stuff at the moon. Then the fact that there's a difference in gravity causes the moon to drift off of the Earth's time by 58.7 microseconds a day now actually needs to be accounted for to the extent that the European Space Agency proposed last year, and the Biden administration has directed NASA to create this year a definition for lunar coordinated time and get it hammered out by 2026 so that countries and corporations don't send various spacecraft crashing into each other unintentionally because they've failed to account for the theory of relativity. Now, when you've gotten to a point where you're talking about relativity and time zones on a different celestial body than the one you currently reside on, you realize that, again, this is a situation where you should absolutely not manage all of this yourself manually. Apple is hooked into the official list of all time zone changes that come from the international organizations that coordinate all of this. And they have a really easy way to get all of the time zones that the system currently knows about. And sometimes that reflects national politics, such as China having only one time zone, despite being roughly the same width as the continental US, which has 4 time zones. And sometimes it can get incredibly local if it needs to. The American state of Indiana, which is only 140 miles wide, has 8 different named identifiers for time zones to account for local differences in the handling of daylight savings time, or as people in Indiana call it, fast time and slow time. In the South American country of Argentina even tops that with 12 different named time zones. And again, you do not want to manage this yourself. Luckily, in addition to the auto-updating current calendar, you can grab the auto-updating current time zone to figure out exactly what time you need to display everything if you're trying to display things in the user's time. And this is part, again, of why UTC is so useful. Because if you're storing, to use an example from earlier this year, the takeoff and landing times of a flight from New York to Singapore, which takes off at 10 p.m. one evening in New York, and then lands at 5 a.m. 2 days later in Singapore, even though 18 and a half hours have actually elapsed, it could be really hard to figure out how to display that in a calendar. But if everything is stored in UTC, it's really easy to figure out exactly what time things need to be displayed in that calendar by applying an offset of their time zone from UTC. Wait, did I say UTC? Because if you actually instantiate a time zone with the UTC identifier, then turn around and print that identifier back out, it lets a nasty secret out of the bag. UTC is actually GMT under the hood. You remember that thing that y'all invented to try to get trains to show up on agreed upon times? It's back. And the technical reason you'll hear about this is that GMT is an actual time zone that is actually used in certain countries for various parts of the year. And UTC is a standard which is based on GMT. And so any calendrical calculations you need to do will actually be based on the deviation from GMT, since you can't calculate a deviation in time zones from a thing that isn't technically a time zone. I kind of hate this explanation because it is way, way farther into the weeds than you should have to get in order to understand what you need to do to make these calculations. But it leads me nicely into a couple of, general pieces of advice I found to be helpful in dealing with dates and times. The simplest one is to only bother working with the components that you actually need. When I was working on auto-generating calendars for Zinnia, the journaling app that I work on, I made a separate struct that just hang on to the year, month, and day for a date. I needed the calendar and date components objects to do all of the math of what the next day was and how many days were in a given month in a given year. But the only things you actually needed to make a calendar display the dates in a month are the month, the day, and the year. And it doesn't matter what time or time zone you're dealing with. The month, the day, and the year don't change for this use case once they're generated. So those components were the only ones I actually ended up using. Especially after a talk like this one, where you learn exactly how complicated this can all be, it's unbelievably easy to overthink all of this and do way more work than you actually need to if you're not careful. You have to step back and look back at what actually matters for your particular use case and only deal with the pieces that you actually care about. However, when you start dealing with more complex aspects of dates, especially when time zones start getting involved, it turns out it's also incredibly easy to underestimate. And whenever something is both easy to underestimate and overestimate, the best way to find out if you've correctly estimated is to test the hell out of what you're doing programmatically against what you, as a human living in your calendar and time zone, know about what to expect when certain things happen. And obviously, you cannot test every single time that ever happens. That would result in infinitely long tests. But there are a few places where you can get a lot of feedback on whether you're handling things properly. The first is when you create a date in one time zone and you read it into another. This is a great way to make sure you're storing and pulling things out properly, although one piece of advice I have for writing these tests is to watch out for what time your continuous integration machine or container thinks it is. If your tests are passing locally and failing on CI, you are probably creating dates in a way that is specific to the local time zone of the machine. Instead, use a calendar you set up manually in your tests to ensure that you always know what calendar and time zones things are being created. The next place to add tests that gets you really good bang for your buck is when one of the date components suddenly becomes lower than it bid. For example, when the end of the day rolls over, hours go from 23 to 0. When the end of the month rolls over, the number of days goes from somewhere between 28 and 31 back down to 1. And when the year rolls over, suddenly the number of months rolls back from 12 or 13, depending on the calendar, to 1. Especially when you're doing date math, these are really, really helpful things to test to make sure that you're getting the answers that you're expecting. Another place to test is when you get things that only happen once in a great while, but at defined times. Things like the rollover from February 28th to 29th to March 1st in leap years for the Gregorian calendar, or whatever years in lunisolar calendars that wind up having an extra month to bring them back in line with solar calendars. And then there's the most infamous case, which is, of course, daylight savings time, that point where we arbitrarily jump forward or fold back an hour because someone in the early 1900s thought it would help farmers save electricity or something. In fact, this leads me to a fun example of the subtleties that testing can uncover, because I messed this up when I was first writing this talk, and only because I added tests around the daylight savings rollover did I realize anything was actually wrong. So to start with, I was working with two different methods around moving a date around. Getting a date from a set of components, and then getting a date from a set of components, then getting a second date by adding a set of components to that date. Now, what I wanted to do was to get an arbitrary number of the next n hours so I could use them to display an hourly schedule, not dissimilar to this one that you see in the macOS calendar app. So in my first stab at this, I was using the API that gets a date from a set of components and then adjusting the components by adding whatever number of hours I needed into the components. By default, if you create a set of date components indicating that you are at March 9th at 25 hours, what you'll actually get back is March 10th at 1 hour. Seems legit, right? My other work wound up using this other method, which is the date by adding components API. In this method, you're still doing a loop, but in this loop, you take the original date, add a set of date components representing the span of time you want to change it by, and then use that for the updated date. So I had a couple of test cases for this. The first was starting at the current date, then either adjusting components by or adding 12 hours to the given date. And the second one was checking what we call in the United States the spring forward, when daylight savings time begins, 2 a.m. Eastern time, March 10th of this year. The date displayed to the user suddenly moves ahead from 1 a.m. to 3 a.m. So when I ran the tests for the current date, which at that point was January, I got basically what I expected, which was that in both cases, the output was exactly the same. So these tests passed immediately. And they passed for every rollover I tried, right up until I hit testing the daylight savings change rollover. So in that case, when you look at the results, you'll see that when you add the components representing a span of time, you go to midnight, 1 a.m., then you get that jump to 3 a.m., then 4 a.m. And this is what you would expect, so this test passed. However, when you're adjusting the components, you get this very weird set of results that says, okay, it's 1 a.m., it's got that expected jump to 3 a.m., but then it's 3 a.m. again, and then it's 4 a.m. And that ain't right at all. So I was very confused by this result, and I was like, okay, what am I missing here? So I reached out to Dave DeLong, who, by dint of volunteering to fix a bug with NS Date Picker about 13 years ago, wound up knowing way more about how dates and time work than pretty much anybody else in the iOS ecosystem. He has an excellent talk from last year's NS Spain conference called The Temporal Axis of Space-Time, drawing really interesting parallels between maps and dates that I cannot recommend highly enough. He also runs the invaluable resource, yourcalendricalfallacyis.com, where you can learn exactly how many assumptions you have wrong about dates. Usually it's a lot of them. Now, my incorrect assumption here was clearly that these two APIs did essentially the same thing. And after talking to Dave, I realized that is absolutely not true. Because when you're using the adjustment method and calling date from date components, what you're actually telling the calendar to do under the hood is find the closest matching dates to the components you've handed it. And when you apply that to daylight savings change, where you're moving forward an hour in the US, you start with telling it you're looking for March 9th at 25 hours. It says, okay, given the way that hours wrap around today, is what you're actually looking for is March 10th at 1 a.m. It says, okay, March 10th at 1 a.m. But then when you tell it you're looking for March 9 at 26 hours, it says, okay, the way that hours wrap around today is that should be March 10th at 2 a.m. Now, because this is the exact hour of the daylight savings transition, that hour does not actually exist. And so date from components tries to find the next closest thing that does exist, which in this case is March 10th at 3 a.m., which is all well and good until you say the next go around of the loop that you want March 9th at 27 hours. And the way that wraps around, it goes to March 10th at 3 a.m. And it says, okay, that does exist. Here you go, March 10th at 3 a.m. And it's giving you exactly what you asked for according to this API. But when you compare it to what a user would actually expect to see, instead of seeing a jump from 1 a.m. straight to 3 a.m., they see 1 a.m. and then two different instances of 3 a.m. That's absolutely not right. This is why my test fails. So why does this work when you instead add date components to a given date? That's because this API is literally saying, what is the amount of time later than the past in date that you want to see? So when you hand it March 9th at 5 p.m. and ask for 8 hours later, you get March 10th at 1 a.m. And when you hand it March 9th at 5 p.m. and ask for 9 hours later, you get March 10th at 3 a.m. It's no longer searching for anything or trying to match anything. It's just literally adding that amount of time to the original date. So that when you ask for March 9th at 5 p.m. plus 10 hours, it gives you the expected March 10th at 4 a.m. And so it was reassuring to get a right answer and to finally be able to understand why I got the right answer. But the fact that you can have an answer that's right about 99.9% of the time and still royally screw up daylight savings time is basically why I drink. And also why Randall Munroe of XKCD drew this cartoon that should essentially describe the evolution of your thinking about dates and time throughout this talk. Because the difference between two dates and time are impossible to know and a sin to ask. So this is why we've also finally come to the obligatory summary slide where I remind you all what the hell my actual points were in this talk. So in this talk, you learned that computers think about dates in a linear and very specific fashion, while humans think about dates in a whole lot of different weird ways, influenced by history and politics and Julius Caesar and the popes of the 1500s and the moon and the sun and the railroads and the telegraphs. And because this all gets monstrously complex, you should take advantage of the foundation APIs, whether within UIKit and AppKit, or within the format style API, or in the new open source version of Foundation, to handle as much of what you want to try to do as possible. And this includes letting Apple figure out what date and time styles would make the most sense to display to a user, given their locale, their time zone, and their calendar preferences. And finally, no matter how well you think you know these things, you will find something subtle that you messed up when you test transition, especially for daylight savings time. So test the ever-living crap out of them. One final thing I just want to say, it's a very personal note. I want to dedicate this talk about time to a guy who did not get nearly enough of it. That's my cousin Mark. The left is me and him around 1990. The right was just this past Christmas. Last year, he was diagnosed with a type of extremely aggressive brain cancer called glioblastoma. Unfortunately, he wound up on the shit side of the one-year survival statistics in March at the age of 38. He was a great guy. He was a colossal Star Trek fan and someone who was deeply loved by his friends who honored him with this absolutely amazing communicator flower arrangement at his funeral. And Mark loved beer. It was one of the things me and him bonded over. He never really liked getting drunk, but he loved trying every different beer he could get his hands on. He loved the app Untapped, and he would always make sure to check in any new beer he had. And in his eulogy, his best friend noted that if you were to try one new beer a day, starting that day, it would take you more than a decade to catch up with Mark on Untapped. So losing this guy really sucked. However, there's some really promising research going on right now that could help a ton in the future to prevent anyone going through what he went through. So if you like this talk, do me a favor, throw a couple quid at a foundation in your area that deals with glioblastoma. I've included links here to the UK's brain tumor charity and to the American Glioblastoma Foundation as well. Next time you go out to have a pint and find something deeply weird that's actually really, really good, raise a glass to Mark. I'm sure he'd have loved to taste. Thank you very much for listening, and I hope you all enjoy the rest of the conference.